In this work, we focus on elastoplastic surfaces that require attention to deformation in the thickness direction. Deep drawing is a prime example where sheets of metal are irreversibly deformed into desired shapes while preserving their original volume. As a result, in-plane deformations induce deformations in the thickness direction as a response. Accurately predicting plastic deformations of these surfaces is a challenging problem. A natural discretization choice for simulating these structures are linear prisms. These elements provide the simplest formulation of a solid shell element. They interpolate displacements linearly in plane as well as through the thickness, making them efficient to compute. Bending is captured as through the thickness variation of in-plane strains that induce both tensile and compressive stresses. For nearly incompressible materials or metals undergoing plastic deformations, these stresses must be compensated by linear stresses in the thickness direction. Linear prisms cannot capture this behavior. While linear prisms can qualitatively capture deformations of moderately thick elastic structures with low Poisson's ratios, they struggle as the material tends towards incompressibility, resulting in overly stiff behavior. For elastoplastic simulations, this limitation translates into overprediction of spring-back, the tendency of the material to revert to its original form. Additionally, strain that is not compensated in the thickness direction is incorrectly assigned as in-plane shear strain, resulting in visible artifacts. For more complex boundary conditions, linear prisms may fail entirely. To address these issues, we propose the Q3T prismatic element. We prioritize efficiency by keeping the element's linear interpolation in plane and improve its performance for volume-preserving materials by interpolating displacements quadratically through the thickness. This modification introduces 3 new nodes at the midsurface of the element, slightly increasing its complexity. In return, we obtain an efficient solid shell element that captures the behavior of elastic materials with high Poisson's ratios more accurately, all while using a single layer of elements through the thickness. As demonstrated by our experiments, Q3T prisms qualitatively match the springback prediction of more complex solid shell element formulations. Thanks to their linear interpolation of strains through the thickness, pure plastic bending deformations are accurately captured. Our element successfully handles complex scenarios involving non-zero Gaussian plastic bending deformations. And captures fine details such as the wrinkling of this metal cup. Thank you for watching.